Chapter 7 Gases, Liquids, Solids, and Phase Diagrams. Section 7.5 The Clausius-Clapeyron Equation. At any point on the existence line between two phases, alpha and beta, these two phases coexist at equilibrium. Here's an example. So we have this coexisting line between the liquid phase and the gas phase. So any data point on this line, you have a equilibrium between the liquid phase and gas phase. These two phases coexist, and also the molar Gibbs energy of the liquid phase equals the molar Gibbs energy of the gas phase along this line, and therefore we have this equation. In general, we'll just say alpha phase and beta phase. The molar Gibbs energy of alpha phase is equal to the molar Gibbs energy of the beta phase at this specific pressure and temperature on the coexistence line. And also we can find another data point on the same coexist line. We just need to slightly perturb this pressure and temperature. Now P becomes P plus dP, T becomes T plus dt. So at this new data point, with both pressure and temperature being disturbed by an infinitesimal amount, we still have molar Gibbs energy of the alpha phase equals the molar Gibbs energy of the beta phase. Now we'll take the difference between these two equations. The left hand side here minus the left hand side, the right hand side minus the right hand side. If you look at this minus this, that's the change of the molar Gibbs energy of the alpha phase when the pressure and temperature are slightly changed to P plus dP and T plus dt. Because Gibbs energy depends on pressure and temperature, and because dG is equal to negative SdT plus VdP, we have the molar Gibbs energy change, which is negative molar entropy dt plus molar volume dP for the alpha phase as the difference between this left hand side and this left hand side. On the right hand side, we do the same thing for the beta phase, and we have negative molar entropy dt plus molar volume dP for the beta phase. Now we have alpha phase and beta phase. And now we will rearrange this equation so that dt appears on one side, dP appears on the other side. So we have over here the molar entropy of the beta phase minus the molar entropy of the alpha phase times dt equals the molar volume of beta phase minus the molar volume of alpha phase dP. This equation holds true for just any coexisting line between two different phases. Now we can have dP over dt. It's simply the change of the molar entropy over the change of molar volume in the transition from the alpha phase to the beta phase. So it's written this way. It's delta S sub m from alpha to beta over delta V sub m from alpha to beta. This m stands for molar. We're looking at alpha to beta transition. Therefore, we have beta phase minus alpha phase. Beta is the final state, alpha is the initial state in this transition from alpha to beta. And we have expression for dP over dt. dP over dt is almost always positive. You can see this is pressure versus temperature. Let's look at this line. This line has a positive slope. That means dP over dt is positive along this coexistence line. Same for this line, positive slope. Over here also positive slope. For the alpha to beta transition, dP over dt is equal to the molar entropy change divided by the molar volume change. Usually the molar entropy change and the molar volume change have the same sign. So they can be both positive or both negative, and that means dP over dt will have to be positive. But there is one exception. That's when water undergoes the fusion process, and then we have molar entropy of this fusion process greater than 0, because the molar entropy of liquid water is larger than the molar entropy of ice. However, we know the density of liquid water is higher than the density value of ice. Therefore, the molar volume of liquid is smaller than the molar volume of solid. So in this fusion process of water from ice to liquid water, delta entropy is greater than 0. Delta volume is less than 0. So over here we can see dP over dt will have to be negative. What if you are looking at the freezing of liquid water? Still dP over dt is less than 0. But when liquid water freezes, the molar entropy is decreasing, the molar volume is increasing. Still dP over dt is less than 0. This is the only exception. For any other substances, delta S and delta V have the same sign no matter what kind of transition you're talking about, whether it's fusion, whether it's sublimation or vaporization. You get positive slopes for this dP over dt slope of the coexistence line. And again, there's one exception, that's water in its fusion process or freezing process. Again, if we are looking at a phase transition from phase alpha to phase beta, dP over dt is the molar entropy change over the molar volume change. When alpha and beta, in this equation, alpha and beta can be just any two of the three phases. They can be solid, liquid, or gas phase. There are 6 types of phase transitions. From solid to liquid, it's called fusion or melting. From liquid to solid, it's called freezing. From solid to gas, it's sublimation. From gas to solid, well, there are 3 words: desublimation, deposition, condensation. From liquid to gas, it's vaporization or evaporation. From gas to liquid, it could be condensation or liquefaction. Again, you can see this condensation here and here. You see condensation from gas to solid, condensation from gas to liquid. So sometimes you better specify the 2 phases if you're talking about a condensation process. When 2 phases are at equilibrium at a given temperature and pressure, we have this equation. Since the Gibbs energy has reached the minimum, I want to say the molar Gibbs energy of the alpha phase equals the molar Gibbs energy of the beta phase, and then there's no change, no further change to this molar Gibbs energy of the substance. It's already reached the minimum, and therefore we have delta G of the transition is equal to 0, or delta G sub m of the transition is equal to 0. Remember, G is defined to be H minus Ts, therefore delta G is delta H minus delta Ts. At a given temperature, you can treat this temperature as a constant, therefore delta Ts is simply T times delta S, and this is 0. And now we have this equation: the enthalpy change in this transition process is equal to temperature times the entropy change of this transition process. Or you can say the molar enthalpy change is equal to T times the molar entropy change of this transition process. And given this, we can rewrite this equation: dP over dt is equal to the change of molar entropy over the change of molar volume. and over here on top, this molar entropy change is simply molar enthalpy change over temperature. So we can have this equation as well. This equation can be used to determine the PT slope of the coexistence lines. When two phases are at equilibrium at given temperature and pressure, first we have this equation. dP over dt is equal to the change in molar entropy over the change in molar volume. How did we get this? Again, we were analyzing two data points on the same coexistence line. The first data point is at pressure P and temperature T. The second point, we have P plus dP as the pressure and T plus dt as the temperature. And we assume the molar Gibbs energy of the two phases are the same on these two data points, because we're talking about the equilibrium between two phases. Let's say we have phase alpha and phase beta. So at PT, these two phases have the same molar Gibbs energy. At P plus dP and T plus dt, these two phases still are at equilibrium, just a different equilibrium. And from that, we can derive this equation. dP over dt is the molar entropy change over the molar volume change. And now, if we're talking about equilibrium, we have delta H equals T delta S, because delta G should be 0, and therefore the change in molar entropy is the change in molar enthalpy over temperature. This T is the transition temperature. Now let's look at two specific phases between liquid phase and gas phase. If there is equilibrium, and then we can simply derive this equation further. So first, dP over dt is the molar enthalpy change over T times molar volume change, and then we can actually estimate this molar volume change. Assuming the process is from liquid to gas, it's called vaporization, and then this change in molar volume is the molar volume of gas minus the molar volume of liquid. Now, the molar volume of the gas phase is usually 1,000 times larger than the molar volume of the corresponding liquid phase. So we can neglect this part. The molar volume of liquid can be neglected. And then we have approximation sign here. It's delta H for the vaporization over TV of the gas phase. And then, because we know PV is approximately nRT, therefore the molar volume of the gas is roughly RT over P. We're making another approximation here. Now, this molar volume of the gas phase is roughly RT over P. We replace the molar volume V of the gas with RT over P. And now we have this expression. We have P over here and then RT squared on the bottom, and also on top there is molar enthalpy change. So now we have actually a differential equation to solve. To solve a differential equation like this, usually we will first identify the variables pressure and temperature, and somehow you need to move the pressures on one side and temperature on the other side before you integrate both sides. So this is what we're gonna do. We look at this equation, and we decide to divide both sides by pressure, and then pressure here will be moved here, and then we multiply both sides by dt. Now we get this equation. dP over P is equal to the molar enthalpy change over R times dt over T squared. Again, from here to here, all we did was we divided both sides by pressure and we multiply both sides by dt. And we have this equation. Now we can integrate both sides of this equation. Again, we'll integrate both sides of this equation. The integral of dP over P is equal to, well, the integral of this part. And the molar enthalpy change in the vaporization process is approximately a constant within a narrow or even moderate temperature range. So if the temperature change is not too significant, we may treat this enthalpy, molar enthalpy change, as a constant. That's why I took it out of the integral. And we integrate both sides, we get the natural logarithm of P2 over P1 is equal to negative molar enthalpy change in the vaporization process over R times 1 over T2 minus 1 over T1. This is because the integral of 1 over T squared is negative 1 over T. So by looking at this equation, we know the boiling point of a pure substance is always higher under a higher external pressure. This is because the molar enthalpy change in a vaporization process, or so-called enthalpy of vaporization, is always positive. So this is positive, R is positive, and then if T2 is greater than T1, we have a negative value here inside the parentheses. But then there's another negative sign, and then therefore P2 is greater than P1. Alright, what if P2 is greater than P1, and then we can derive this, the sign of this has to be negative, so T2 is greater than T1. So again, the vapor pressure of a liquid is always higher at a higher temperature, and also, well, the boiling point of a pure substance is always higher under a higher external pressure. So both statements are correct. For water, we may choose the normal boiling point of water as the reference to compute its boiling point under any other pressure. So water boils at 100 degrees Celsius, so we plug it in here under 1 atm pressure, so we plug in pressure here. Now we have a relationship between the pressure and the boiling point. If you have a higher pressure, you'll have a higher boiling point. Lower pressure, lower boiling point. The molar enthalpy change of vaporization, or so-called enthalpy of vaporization, can be looked up. It does change a little bit when you change the temperature, but approximately you can treat the enthalpy of vaporization as a constant. It's approximately a constant. And now let's look at the graphical representation of this equation, or this equation. It's right here. So you can see the natural logarithm of P and 1 over T has a linear relationship. Over here I'm using P over P naught, but you can of course use some other references. For example, for water, you can replace this P naught with 1 atm, and then you can somehow use this normal boiling point of water to get the y-intercept. So by looking at this equation, what's the y-intercept? It's just negative enthalpy of vaporization over R, and then divided by this temperature. That's the y-intercept. And the y-intercept has another physical meaning, because if you look at this, the enthalpy of vaporization divided by the temperature of vaporization is equal to the entropy of vaporization. So you can see this expression here. It's just equivalent to this part divided by negative temperature. Same thing. Again, when the liquid and gas phase are at equilibrium, the Gibbs energy of vaporization is 0. Therefore, the enthalpy of vaporization is equal to the temperature of the transition, or actually the boiling point multiplied by the entropy of vaporization. Again, you just need a reference. Over here I'm using 1 atm and 100 degrees Celsius as the reference for pure water, but you can also use 1 bar over here and then the corresponding boiling point of water here. So what's the boiling point of water under 1 bar pressure? Because 1 bar is slightly smaller than 1 atm, the boiling point of water should be slightly smaller than 100 degrees Celsius. And actually it's indeed slightly smaller than 100. It's 99.6 degrees Celsius. Pure water boils at 99.6 degrees Celsius under 1 bar pressure. Water boils at 100 degrees Celsius under 1 atm pressure. 1 atm is approximately 1.3% higher than the 1 bar pressure. So again, this graph tells you the natural logarithm of P is linear with 1 over T. That's why we can plot LMP versus 1 over T and determine the slope and y-intercept. The slope is negative enthalpy of vaporization over R. The y-intercept is the entropy of vaporization over R. After you get the slope, multiply that by negative R, you get the enthalpy of vaporization. After you get the y-intercept, just multiply the intercept by R, you'll get the entropy of vaporization. And delta H over delta S, you get the temperature of vaporization, or you can say the boiling point of this vaporization process. At the liquid gas equilibrium of pure water, we have this equation. Again, water boils at 100 degrees Celsius under 1 atm pressure. Now we can determine the boiling point of pure water at 2 other different pressures. The first is lower than 1 atm, 0.03 bars. The second one is higher than 1 atm, it's 2 atm. You're given the molar enthalpy of vaporization, or simply enthalpy of vaporization in kilojoule per mole at the normal boiling point, and then we can plug in this pressure of 0.03 bars on top. So we have that on top. 1 atm is 1.013 bars, so we have these 2 numbers. We plug in the enthalpy of vaporization and then R here, and then 1 over T minus 1 over 100 degrees Celsius. We see only one variable here. We can solve this equation easily. I used Wolfram alpha to solve this equation. We get temperature 294 Kelvin, that's 21 degrees Celsius. What's the physical meaning of this? Well, there are 2 interpretations. One is this: at 0.03 bar condition. So if the external pressure of pure water is 0.03 bars, water can boil at 21 degrees Celsius. Therefore, the boiling point of water is 21 degrees Celsius under this reduced pressure, 0.03 bars. Actually, there's another physical interpretation. So at 21 degrees Celsius, when liquid water and water vapor are at equilibrium, well, the partial pressure of water vapor should be 0.03 bars. Now let's look at the higher pressure. If the pressure is 2 atm, we expect to see a higher boiling point. Again, we plug in all the numbers. 2 atm over 1 atm over here. This is 1 over the boiling point under 2 atm pressure minus 1 over 100 degrees Celsius. We plug in those values for the enthalpy of vaporization over here and the value of R. We solve this equation. This T is actually 394 Kelvin, or 121 degrees Celsius. So the boiling point of water now is higher than 100 degrees Celsius. That's why if you use a high pressure cooker to cook food, for example rice, it's gonna take much less time, only because when you use a high pressure cooker, the boiling point of water becomes 120 degrees Celsius. It's much higher than 100 degrees Celsius, and rice can be cooked much faster at this higher temperature. Again, the boiling point of water is not just 100 degrees Celsius. It is 100 degrees Celsius under 1 atm pressure, but actually the boiling point of water can be within a very large range. The boiling point of water is 21 degrees Celsius under 0.03 bar pressure. The boiling point of water is 121 degrees Celsius under 2 atm pressure. What's the lowest possible boiling point of water? It's actually 0.01 degrees Celsius. If the pressure is as low as 0.006 atm pressure, actually this is the triple point of water in the PT phase diagram. Below 0.01 degrees Celsius, you will not be able to get the liquid phase of pure water. You can get ice or water vapor. It depends on the pressure. Now, below 0.01 degrees Celsius, if you have a high pressure, then ice is more stable. If you have a really low pressure, then the gas phase is more stable.